There once was a man called Enos, who had an extraordinarily large penis. He stuck in his thumb and pulled out some cum and shot his way off towards Venus. Greetings, the Astro 30 here yet again with a sort of different video. It's more of an experimentation video rather than making anything constructive. But discrete operational amplifier. Well, first off, an operational amplifier, or as they're often just referred to as op-amps, are usually little 8, 14, 16 pin, sometimes single inline, dual inline devices, integrated circuits, which you can buy from ranging from about 20 cents up to $10 for very low noise ones. And they became very popular around about the 70s when the good old LM741 was released. Originally, operational amplifiers were designed using vacuum tubes back in the 60s for computer systems that were built mainly to do arithmetic operations, hence the term operational amplifier. That's where it got its name. But besides the history lesson, we're going to take a look at this discrete operational amplifier, test it out and see how well it actually performs. Oh, excuse me. Now the output topology of this is class A, so it'll have very little crossover distortion, well actually no crossover distortion, and very little distortion at all. However, being class A, it's going to have a fairly high quiescent current draw or idle current draw, so you can imagine several of these all connected up to the same power supply in, say, a preamp for instance. You'd be getting very close to 1 amp of current draw at idle with this type of topology. So it wouldn't really be used for anything productive or constructive, or in anything that was really important where you want minimal current draw and stuff. But it is good for testing and experimenting with. So what we're going to do, well actually what I'm going to do, I don't know why I keep saying we, it's only me doing it and I'm presenting it. This is not the royal we, this is not the corgis and I declare war. So yes, anyway, I'm going to build this up on a piece of breadboard and I'm going to run some tests on it. First test is going to be, well, open loop gain. That is where the output is not connected to any of these inputs. And do a measurement on an oscilloscope for that. I'm also going to do a closed loop gain, having a resistor between the input and output. And then I'm going to do 2 configurations, and non-inverting amplifier with a gain of roughly 4.5, 5.5, and see what the output is, and then do an inverting op-amp stage with a gain of the same 4.5, and then compare that to an actual ready-made operational amplifier being the 5532. Now most of us already know what the specs of the 5532 is, and they're pretty good. The only things I can't measure with this circuit is distortion. Well, my new Digitech oscilloscope does have the FFT spectrum analyzer function on it, but I haven't figured out how to use it yet. So I can't measure distortion or total harmonic distortion, and I can't measure slew rate. So, but I can imagine that the slew rate of this is going to be pretty average. So anyway, let's get this breadboarded up, and yeah, we'll run some tests on it. I should say I will run some tests on it. Okay, about half an hour later, I've got it all breadboarded up, as messy as it is. I've got it hooked to the DC power supply, set to plus minus 15 volt. and I haven't turned it on yet or anything. I'm just basically going to turn the load on and see if anything goes bang, and also see what our current draw is. So without it hooked up to a signal generator or an oscilloscope, I'm just going to turn the load on and see what the draw is. Absolutely nothing, which is a little bit disappointing. I would have expected some form of current draw. Okay, I've hooked up an oscilloscope to the output and our ground reference, and yeah, we are getting a output with the blurt test. Oh, for fuck's sake. It is, however, in open loop gain, so we will just quickly look at what that is. Open loop gain is basically you take an op amp in this configuration, non-inverting. We have a positive input here, a non-inverting input, which is where our signal is going to go in. We've got the output. We've got a resistor gain, which could just simply be the negatives going straight to earth. But for now, I've got a 4K7 there as RG, and there is no negative feedback. So the open loop gain means there is no actual feedback path from the output back to the input. And in an ideal world, with an ideal op amp, the open loop gain should be infinite. But for this little circuit, I doubt that to be the case. Okay, so after shorting the output and blowing one of the BC549 transistors up, yeah, lovely. Don't dick around with it powered up. The open loop gain of this with a 22K resistor going from the positive input to ground as a biasing resistor at plus minus 15 volt is absolutely crap. We're looking at a voltage peak to peak output of 214 millivolts. That's not a great deal. This is all with 1 volt input peak to peak. In fact, that open loop one I just measured, I reckon that was just noise. Closed loop gain, we're looking at, albeit it's flat topping early, we're looking at 11.35 volt peak to peak at 1 volt in. But as I say, it's flat topping early, so what I might do is adjust the amplitude down to 500 millivolt and see if the flat topping goes away, which apparently it does not. So yeah, that's pretty nasty clipping. It's not a perfect sine wave there. I will demonstrate what closed loop gain is in a second, but yeah, it's not the output capacitor doing it. And because this is a Class A output stage, don't forget to have an output capacitor. So closed loop gain is the good old fashioned non-inverting amplifier configuration with a feedback resistor from the output back to the inverting input. And I've basically got a 4K7 and a 100 K resistor there respectively. So if we do a bit of math here, we've got a 100K, which is 100,000 ohms, divided by 4,700, which is 4.7K. That gives us that, plus 1. That gives us a gain of 22. So if I wanted a gain of 10, that would have to be, or gain of 11, that would have to be a 10K for the feedback resistor, or I should say the resistor gain here, RG, would have to be 10K, and RF would have to be 100 to make it, well, a gain of 11. So we've got a gain of 22, so that might be a little bit high. So we'll change our feedback resistor to, well, okay, 47K divided by 4,700. What was that? That equals a gain of 10. So plus 1, a gain of 11. So, okay, that'll give us a gain of 10, or gain of 11. Will that solve the flat topping clipping? Let's find out. Well, I've got the 47K in there. Yes, we've got reduced gain, but we've still got that nasty distortion. So with 1 volt peak to peak coming in, we've got roughly 5.7 peak to peak coming out. So it is working as an amplifier in the non-inverting direction. So now to hook it up as an inverting amplifier and do the tests again. So, well, with it hooked up in inverting mode, with a 4K7 on the input, it's very square wave. So as we can see, we're getting about 15.2 roughly peak to peak out, but it's clipping badly. And as I reduce the amplitude to say 200 millivolt, it's still square wave. It's horrible. This as an amplifier is absolute shit. Yeah, that's a brilliant fucking amplifier, that is. I don't know really what to tell you, except that as an op amp, well, in any shape or form, it's not good. It's absolutely terrible. Okay, so if I just turn the supply off, get in the way of the camera again, and just remove the end of the feedback resistor so it's not connected to the output, we have absolutely no output. So open loop gain, nope. So I'm just going to get in the way of the shot again and plug this back into its output, if I so can. Right. Yeah, as an amplifier, that's crap. And this is the whole entire point to this video, is not to actually say, okay, yeah, this is great, we'll make this and it's a great working replacement for an op amp and it's all discrete transistors, etc. No, it's experimentation. Let's measure the thing, see how it performs. Can we improve it? Well, I'm probably not going to bother. However, there is one thing that can be changed, maybe to improve the output swing or get rid of some of the distortion, is I've got a 47 ohm resistor here. Now, it should have been a 68, I don't have any. I can change it to a 100, but if I change that resistance and increase it, it may or may not get rid of that flat topping. So let me just change that to a 100 ohm resistor respectively. Now the reason I say it should have been 68, because I've put a link in the description to where that circuit came from. It comes from Rod Elliott's article on Discrete Operational Amplifier. I'm not building it to, you know, say, oh yeah, it's a great circuit. I'm just building it to test it and see how well it operates and how well it doesn't operate. Nope, made absolutely no difference. Okay, so I suppose the burning question is, what does this actually sound like with audio? And I can guarantee you one thing, it'll sound like absolute shit. Okay, so considering that the op amp is Class A, it's only fitting to use a Class A power amplifier module to hook it up to a speaker. So we'll turn the power supply on, and I'm just going to touch the input capacitor. That doesn't sound very nice at all. So yeah, it sounds pretty crap actually. So we can imagine what it's going to sound like to a input source. So for that, what I'm going to do is I'm going to take my DDS and I'm going to take it down right down to say 50 millivolt. Millivolt. Did that even change? I don't know. Yeah, apparently. And then I'm going to hook up the DDS. So now I'm going to change the output to say 100 millivolt. Yeah, that's nasty. So we can hear straight away that that sounds like absolute crap. Well, it turns out I had the feedback resistor connected to the wrong base of the wrong transistor. I had the base of the first transistor here going to ground, as it should have been, and I also had the feedback resistor going to the same point. Yeah, that's not going to work. Now, unfortunately, whereas the output voltage is a lot less, it's peak to peak now of about 2.9 volt roughly, which is a little bit better than the 11 that we had before. Basically, we had open loop gain. However, the sine wave is disgusting at 1 volt, and even turning the gain down, yeah, it's clipping badly. It's as an amplifier, it's not working very well at all. So, yeah, I really need to hook it up to an audio source other than the signal generator. I don't know if you can hear that, but listen to the amount of hiss coming out of that speaker. So, I know in inverting mode that is crap. So what I might do is I might hook it up back in non-inverting and see if there's a difference. Okay, it's hooked up in non-inverting mode. I've got a little, it's actually a linear 20k pot there as a volume control. It's not the best solution. It's also a bit DC scratchy, but it is working. But if I touch the control, obviously I'm injecting radio frequency into it. But I can control the volume to a point, so I can hear that the signal at 1 volt going in is pretty clean. So yeah, let's hook it up to a source of audio and just see how it sounds coming out the speaker. Okay, here we go. Okay, I can hear there is a bit of distortion there. So as a replacement for an op amp, no. As an experiment, yeah, it was okay. It just did prove that, well, the concept works, however, it doesn't work very well. So, let's use an NE5532 op amp instead of that discrete circuit, and I'll run the tests with the oscilloscope again, and well, we can see exactly what's going to happen. And then I'll do a music test again with the op amp instead of the discrete circuit, and then I'll come back with my final conclusions. So in non-inverting mode, our closed loop gain is 6.16, we'll say, volt, peak to peak. Okay, so I've got an NE5532 hooked up. This is the feedback resistor in mid-air here. It's now in non-inverting with open loop gain. And immediately we can see on the oscilloscope we have a big difference compared to the discrete version. We now have roughly 31.6 volt peak to peak with clipping at open loop gain. So it's still running on plus minus 15 volt. So it's clipping because, well, it's trying to go into infinite gain, which it cannot do. And the good thing about these op amps is they don't care if it's powered up and you short something, unlike the transistor one, which I blew one of the transistors doing that. However, I will turn the load off before I connect my feedback resistor from pin 2 to pin 1. Now if I can just get this to go in there. Now I'm using exactly the same input and output capacitors as I was in the first test. 1 microfarad electrolytic, 1 microfarad crossover. Makes no real difference, but yeah, I'm just making sure that I haven't got an impedance problem on the oscilloscope. So now closed loop gain, we've got 11.76, which is a big difference from the discrete version too. And our sine wave is relatively clean, which is a lot better than the first results. Okay, so that's fine in non-inverting mode. We'll hook it up in inverting mode and do the two tests again. Okay, in inverting configuration, I did start out with a nice square wave and it was about 30 odd volt, but it seems to be falling off. Just hang on 2 secs, I think I fucked something up. Okay, so we have got 31.6 again peak to peak in open loop configuration with it in the inverting configuration. And again we take note that it's square wave because, well, it's clipping and it's trying to go infinite gain, which it cannot do. So we'll hook it up into closed loop gain. Now the resistors are exactly the same. It's a 4K7 and a 47K resistor respectively. So in non-inverting mode that should be a gain of 11, and which is what we had with closed loop on the non-inverting version. And in inverting we should have a gain of 10. Turn the supply off, and now I'll just connect my feedback resistor from pin 1 to pin 2. So now we've got closed loop gain. Let's see if I can get the damn thing to go into the holes. Okay, that should be okay. Turn the supply on. And voila! We have a nice clean sine wave of roughly 10.5 volt. So there you go. So that just goes to prove a discrete op amp, or that particular design of discrete operational amplifier, isn't any bloody good. Sorry, Rod. I built the circuit exactly the way it was presented in your article, which I'll link in the description, but my test results, yeah, unfortunately, as an amplifier of any description, is crap. Sorry, Rod, but it was a good concept, but it just doesn't work. Even if you change this resistor to 100 ohm and this one to 4K7, because I had a 2K2 there, thought that might have been the problem. But really, all this resistor is controlling is the DC offset at the output anyway. Well, it works, just not very well. It will never replace a linear IC. No way, shape or form. So, now that we know that it's functioning as it should, as an amplifier, well, we know what's going to happen as soon as we connect this either in inverting or non-inverting to the power amplifier sitting over here. It's going to output fine. But we might just do that to close out this video. So to recap the results in a nice little table here before we do the sound test versus the discrete and the NE5532 respectively. In non-inverting configuration, the open loop gain on the discrete was non-measurable. It didn't have any. Closed loop was 6.2 volt peak to peak. Conversely, for the NE5532, the open loop gain was 31.6 volt peak to peak, obviously clipping. Closed loop was nice clean 11.76 volt peak to peak. Conversely, in the inverting configuration on the discrete, the open loop gain was again negligible, non-measurable. The closed loop was a meager 2.9 volt peak to peak, and this is all with 1 volt peak to peak in. Conversely, with the NE5532, well, the results speak for itself. Open loop gain, again, 31.6 volt peak to peak, distorted, and clean closed loop gain of 10.5 volt peak to peak. So immediately by those results we can see a conventional op amp wins each time for its open loop gain capabilities as well as good closed loop gain. The discrete version is just a complete and utter fail as far as I'm concerned. Now with Rod Elliott's design there, he didn't actually build it, I don't think. All he did was he simulated it in Spice, and he concluded that the open loop gain of that particular circuit should be close to the magnitude of 5600. Well, it was nowhere near that. So as I said, I don't think he actually built the circuit on breadboard like I did and tested it. He just did a simulation in his CAD software and came up with those conclusions. With a bit of rejigging of the circuit for non-inverting purposes, it could work okay. The inverting one, well, you saw what the waveform looked like. However, the sine wave is disgusting at 1 volt. So my conclusions to this is no. Okay, so I've got the op amp hooked up to the power amp, and it sounds reasonably better. So I'll hook that up to the audio source via that volume pot and have a listen. Okay, so here we go. Hopefully the level's not too loud. Okay, so yeah, as we can hear, it sounds a shitload better. And that's still in inverting configuration. I could connect it up in non-inverting configuration, do another sound test, but what's the point? It'll work exactly the same way, except it'll be 180 degrees in the correct phase instead of 180 degrees out of phase. But and 1 volt difference in the actual output gain. Anyway, this concludes this video about a discrete operational amplifier, which, by the way, doesn't work. There are very many different incarnations of a discrete op amp. I might explore a few more different designs later, but for this particular design, it's a fail. I wouldn't recommend using it for anything. You could probably use it for a DC amplifier, but as an audio amplifier, no. Anyway, I'm the Astro 30, and if you like this video, please remember to rate, comment and subscribe below. You can always follow me on Facebook and Twitter. The links are in the description as usual. Anyway, this is the Astro 30 saying, see ya, happy operational amplifiers.